Hi everybody, welcome to a new lecture of ITC 255, which is on random variables. Consider the experiment of going to office. We know that the outcomes are late on time or early. Most of the time it's useful to represent the outcomes of the experiments by numbers. Please remember that there are a lot of variables whose outcomes are already represented by numbers, such as the weight of the next customer coming to your market, or recording the time that you need to go to office. There are also a lot of experiments whose outcomes are not primarily represented by numbers, such as the one we have here. In such cases, we use a methodology called random variable to transform the outcomes of the random variable into numbers. Random variable is actually a function defined from the sample space of an experiment to a set of real numbers. And this representation here is the sample space, which is the domain of the function x, which we call a random variable, and b is a subset of real numbers. Remember that if b contains discrete numbers, then x is a discrete random variable. If b contains continuous numbers, decimal values, then x is a continuous random variable. Let's consider the example of the experiment of going to office and define the random variable x from s to -1, 0, and 1 such that x of late is -1, x of on time is 0, and x of early is 1. Remember that these 0, 1, and -1 are just codes that we have chosen for the outcomes of our experiment. Then if we run the experiment 100 times, suppose we get the following distribution: late 40%, on time 10%, and early 50%, and combining this with x, we get that the probability of x getting the value of -1 nearly 40%, of the value of 0 nearly 10%, and of the value of 1 is 50%. Furthermore, we can compute the probability of secondary ones. For example, the probability of x being 0 less than 0 is 50%, and the probability of x 0 or bigger than 0 is 60%. Next, consider the experiment of going to a bakery and counting the number of people waiting in the queue. Repeat this experiment 100 times. As we can see in this distribution table, no people waiting happened 4 times out of the 100, 1 person waiting 10 times, 2 persons waiting 20 times, 3 persons waiting 30 times, 4 persons waiting 21 times, 5 persons waiting 10 times, and more than 5 persons waiting 5 times. So we get this frequency distribution table along with relative frequency, which are actually the estimated probability. Then the sample space for our experiment would be this set S, which takes 0, 1, 2, 3, 4, 5 or bigger than 5. And we already can think that the random variable n, which is defined from S to B, is first of all represented by numbers. And second of all, this is discrete. Hence, the b, which is the range of the random variable n, is the same as the sample space because the sample space is already numbers. We can then calculate different probabilities. For example, the number of people waiting equal to 0 is 4%. The probability that the number of people waiting is more than 5 persons, 5%. The probability that the number of people waiting is 3 or less than 3 is 64%. Like this, we can compute further probabilities. We use a function to present the probability distribution of a random variable, which is defined from b, which is the range of the random variable, to the closed interval 0 and 1, which is the range for the probability function. For instance, f of 0, which is nothing but the probability of n equals to 0, is 4%. F of 1, which is the probability of n equals to 1, is 10%. F of bigger than 5 is probability that n is bigger than 5 is 5%, and so on and so forth. In fact, we can plot the PDF or probability distribution of the random variable n as follows, putting the estimated probabilities for each of these outcomes, namely for 0, 1, 2, 3, 4, and 5, and more than 5 into a histogram. We can see that the probability distribution is given by this histogram. Next, consider the experiment of recording the time it takes you to arrive office. Suppose you run this experiment 100 times and you record the number of minutes you need to reach to office. For example, first day you need exactly 15 minutes, second day you need 14.5 minutes, third day 15.2 minutes, and so on and so forth. And as you can see here, if we define a random variable t from s to an interval from 0 to infinity is the time it takes you to arrive to office, is actually a continuous random variable because the time you need can take any value bigger than 0. In fact, theoretically 0 or bigger than 0. In this case, since arrival time, which is t, takes infinitely many values, hence the probability of each value is nearly 0. In such cases, instead of computing the probability of each value that the random variable would take, we compute the probability that the random variable would take a value in an interval. In other words, we compute the probability that the arrival time is between 15 and 16 minutes. In order to compute such probabilities, we plot the density function of the probability distribution of t, which is referred to as probability density function.